Hello again, welcome back for the questions relating to conduction and convection. There's only two questions for this one. As I said, smaller topic. I've only got a couple of questions, and they actually happen to both relate to conduction because that's one where we can do some calculations on it. Convection will just present you with scenarios and you need to be able to identify them. I don't have one of those specifically for this, but hopefully you can think about that, apply it to different scenarios yourself as well. Also, feel free to read the textbooks and obviously discuss at the workshops and things if you've got any questions relating to that. So here are the questions. We will go straight to the first question, which is about a chili bin or an esky if you're in Australia, or a cooler in the States, or whatever you happen to call it. I'm going to stick with chili bin. You have 1 kilogram of ice mixed with some water and cans of drink, all at 0 degrees Celsius inside a chili bin. So this whole mixture is at 0 degrees Celsius. It's a sunny day and the temperature outside the chili bin is 28 degrees Celsius. If the chili bin is made of 2 centimeter thick styrofoam with a K value, a thermal conductivity of 0.01 watts per meter per Kelvin, and it's got a total internal surface area of 1 square meter, the question is how long until the ice is all melted? So the environment, the sun and the energy in the air is warming up the chili bin. The chili bin allows heat to flow through it, but at a very low rate because we've got this very low K value. As that heat flows through, it'll obviously go into the ice and mixture of stuff inside the chili bin, raising its internal energy. And we've been asked how long will it take to raise that internal energy enough that the ice has all melted. They've also given us the latent fusion of ice, latent heat of fusion of ice, as 3.33 times 10 to the 5 joules per kilogram. So as usual, have a go at this question. Don't just rely on following along with me. I'm going to jump over to the document camera now and we'll get started on the solution. So pause the video if you haven't, have a go at this question and we'll see what we can get out. As usual, first thing to do is to write out what we know and possibly sketch the scenario if you need to. So I'm going to draw a little box. Here's my chili bin. Right, now this is 2 centimeters thick, so it's got a thickness to it, and inside of that we've got our cans of drink floating in some water with some ice in it. Right, so we've got cans of drink with some water and some ice. There's our block of ice. Right, so we've got water and drink and ice. So inside here we're all at 0 degrees Celsius. Outside here we're at 28 degrees Celsius. And so we're going to get some heat flow into, we'll get heat flowing into our object. So the Q will go in. Heat's going in from the outside environment into the chili bin. We've been told that the chili bin is 2 centimeters thick and it's got an internal surface area of 1 square meter. Now, it may be a little confusing at first as to how you would approach this. You might be trying to think about every individual side. But if you did that, if you think about doing every individual side, then you're going to have a heat flow due to this square area, plus this heat flow, plus this heat flow, plus this heat flow, plus this one, plus that one. You can have all 6 sides, and you'd have all heat flow. Yes, we can include the bottom, because if everything in the environment is at 28 degrees C, then the sand will be as well. Sand will be at 28 degrees C. So everything's at 28 degrees C, it means it's getting heat in from all sides. So we can treat all of them the same. But if we do that and add up all the different heat flows, then that's the same as just doing it for the total internal surface area all at once. So we can actually just stick with our formula being Ka T1 minus T2 over L. And we can just use the surface area total here. If you need convincing of that, imagine we had 2 different surface areas, then you'd have Ka1 times T1 minus T2 over L, plus Ka2 T1 minus T2 over L. So this was if we just had 2 areas to concern ourselves with. Then you can see that you can factor out the K and that fraction. So you'd get K A1 plus A2 T1 minus T2 all over L. And that's just the same as the total area, but back in that original formula. So hopefully that convinces you that this means we can just use A equals 1 square meter. And we just worry about the total area all at once. So if we've got the K was given to us, we've got A as the total area, we've got T1 over T2 being 28 and 0, and we've got L being our 2 centimeter thickness. Remembering to turn into SI units, that means that L is equal to 0.02 meters. So that's our scenario. We know everything about it, but the question is what happens as it receives some energy? As this heat flows in, this is not big enough to be a thermal reservoir. We can't assume that the internal energy doesn't change. But what we do know is that as it receives some some heat and it becomes internal energy, it's going to be used to change the phase of that ice. Remember that the temperature is not going to go up until that ice is all melted. And since the question is about the energy needed to melt all of the ice, as soon as the ice is all melted, our scenario stops. So we're never going to have a change in temperature. So we don't have to worry about the temperature changing on either side of this. It's going to stay at 28 on the outside and stay at 0 on the inside. Only once all of the ice is melted would it start to then increase. And once it does that, we're not worried about it because that's beyond the consideration of our scenario. So that means we don't have to worry about T1 or T2 changing. And that means that T1 minus T2 will just be 28 degrees C for the whole problem. Area is 1 meter square, K is 0.01 watts per meter per Kelvin, and length is 0.02 meters. So we know everything for this. So we can actually calculate our heat flow, and we get delta Q over delta T is equal to 0.01 times 1 times 28 over 0.02. So that's the result we get. And that comes out to 14 joules per second. So that's our rate of heat flow, 14 joules per second. But the question the question we've been asked is how long does it take for this ice all to melt? We've got 1 kilogram of ice. So it actually becomes a latent heat of fusion problem. We've got 1 kilo of ice, right? And we've been told that the latent heat of fusion for ice is equal to 3.33 times 10 to the 5 joules per kilogram. If we've got 1 kilo and it takes this many joules to melt 1 kilo, then it's just going to need this many joules. So we need Q equal to 3.33 times 10 to the 5 joules. So we need to provide 3.33 times 10 to the 5 joules, but we're doing it at a rate of 14 joules per second. So we can just divide them, right? If we take this number, this many joules total, divide it by how many joules we get per second, that'll tell us how many seconds it takes to melt, to obtain that much energy. So if we divide them, I'm just going to squeeze it in the bottom of this bit of paper here. That gives us a time of 24,000 seconds. 24,000 seconds. Which, if you turn it into hours, because that's a more useful, if I tell you 24,000 seconds, most people don't have a feeling for how long that takes, but it actually ends up being 6.6 hours, right? Or just over 6.5 hours. So six hours and 35 minutes or something, right? So just over 6.5 hours. That's how long it would take to melt 1 kilo of ice. Of course, in the real world, you're opening and closing this chili bin, and every time you open it, all the air in the chili bin is replaced by hot air from outside, and the overall internal energy will be constantly increasing. Also, there'll be radiation, something we'll deal with in the next topic, that if the sun is hitting that ice, that's going to be absorbing some extra energy that way. So overall, it wouldn't necessarily last that long, but if you got the entire inside of the system to 0 degrees Celsius, everything in there was 0, and you still had a kilo of ice in there, then it would last 6.5 hours if it was all shut like that. Right, so it can take, having a good insulator, the styrofoam insulator is the key here. We had a good low thermal conductivity insulator as our chili bin, then it can mean that we have a long time before the ice melts completely. And that's obviously good. Second question is relating to a copper bar. You've got a copper bar 40 centimeters long, cross-sectional area of 5 centimeters, heated at one end such that it is kept at a constant temperature of 140 degrees Celsius, and the other end is exposed to an ice water mix and so is kept at 0 degrees Celsius. The sides of the copper bar are heavily insulated. That heavily insulated on the sides of the copper bar is just telling us that we're not going to lose any heat out sideways from this bar. We're only getting heat flow from one end to the other, nothing out from one end to the sides. The questions, we have 3 questions here. What is the temperature halfway along the bar? What is the rate of heat flow through the bar? And if the area of the bar was instead 10 centimeters squared, what would the heat flow rate be? So nothing too strenuous here, hopefully. I'll jump back to the document camera and we'll just talk through these, but these ones shouldn't take too long. What is the temperature halfway along the bar? So we've got our copper bar. This end is at 140 degrees Celsius. This end is at 0 degrees Celsius. So we're going to get heat flowing from the hot end to the cold end. If you measured the temperature at each point, at this point it's 0, and I'm going to turn this bar into a bit of a graph. At this end we're at 140, at this end we're at 0, and it would just be a straight line because this bar is completely uniform. And so if you go exactly halfway along, then that would mean that you're exactly halfway up. So you should be at 70 degrees Celsius halfway along the bar, because we're assuming that that bar is nice and uniform. We've been told that it's 5 centimeters square area, 40 centimeters long. Everything there seems to indicate that it's a nice uniform bar. Calculate the rate of heat flow. So question B is the rate of heat flow, which is our delta Q by delta T. And we know that that is Ka T1 minus T2 over L. We know all of that. We've been told A is 5 centimeters squared. We've been told L, which is 40 centimeters. We know the 2 temperatures, and when T2 is 0 degrees Celsius, it's easy because this is just 140 in this case. And we've been told K for copper, not on the question sheet, but we have been given our table of thermal conductivities earlier in the lecture, or you can Google it or find it however you need to. K is 380 watts per meter per Kelvin, so you can look that up. And that means we know everything here. So plug it in, this is just math, we get 665 kilojoules per second. And then the next question, part C, is what happens if we double this area? Hopefully you don't even need to do this calculation again. You can just look at it and say, well, if we double this, that's going to double this, right? It's linear. If you double A, that has to double this, if everything else is the same. So that means that for part C, we just double this. So we get 1,330 kilojoules per second. And that's it. That is the answer to the copper bar question. So that's the end of topic 2. As promised, it was hopefully slightly shorter and simpler than topic 1. And topic 3 will continue on and look at the third heat mechanism of radiation.